This is a video walkthrough of the example script that we provided that demonstrates the TDM technique. So just to orient you, we have a couple things open. This is the OSF website where we essentially use this to store the example dataset. It's not terribly large, it's only 350 megs. And we also have the GitHub repository with the TDM code, as you can see here. And we also have a local folder containing the GitHub repository, as well as a window onto my workstation where we'll be running the code. Okay, so just briefly, let's look over the various components here. The GitHub repository has a README, talks a little bit about dependencies. There are a couple dependencies that you need to download and have on your MATLAB path ahead of time. So this one, K&K utils, as well as GLM denoise. There are a couple external repositories that we include in the TDM repository for your convenience. They're contained in here. These two are necessary, whereas the ICA toolbox, which is a widely used toolbox, is not really necessary. It's only used if you want to perform this sort of alternative ICA procedure, which is demonstrated in the example script. The example script, after running, is shown, the outputs are shown in this link here. This is just a rendering of the HTML output. And we can just scroll through really quickly just to show you what it looks like. So it's a bunch of code and figures that it generates. And this is what we'll be explaining in detail in this little video. Okay, so that takes care of the TDM GitHub repository. And then, as I mentioned, the data set itself is stored on the OSF. Importantly, on this little short wiki page here, there's a documentation of what's contained inside the data set, and we'll look into that in detail in a second. All right, so I have a little MATLAB terminal open here, and let me just make sure we're starting fresh, and I am in a directory with the GitHub repository, and so we're ready to go. So let's open up this example script. Let's scroll to the top. So the first step really just downloads this data set from OSF, which I've already done, so we can just skip it. So let's do this step. We'll just load in the data set and take a look at what's inside. This is taken from one of the data sets reported in the preprint, and it's dataset D2, and so there are several variables in here. The main one is the one called data. So these are 4 runs of preprocessed fMRI time series data, and the dimensionality of each of these elements is a bunch of vertices. So the data have been sort of prepared in surface format, and the columns here are TRs, or time points, and the sampling rate that we've prepared the data as 1 second. Anyway, so let's take a quick look at just some random vertex here, vertex 1000. So we're just going to plot from the first run the time series of one of these vertices. So it looks like something. These are raw scanner units. The design was a sort of a rapid event-related design, so it's not clear whether these little wiggles are an important signal or not. We can also take a look for the same vertex, what happens in the second run, which is, these runs are about 6 minutes long. And it looks like this. Looks okay. Okay, so that's what data is. We also have, importantly, the design matrices. So again, 4 runs, and we have 368 time points, and there's 6 columns. And the reason is there are 6 experimental conditions. I'll show you an example of the experiment. So there's a visual experiment. The subject fixates this dot here. These rings come up and stimulate for 3.5 seconds, and there's a brief gap. This is actually a blank trial, a 4-second blank trial. Okay, here's the next trial, 3.5 seconds. There's a 0.5 second gap before the next trial, 3.5 seconds, a short gap, the next trial, and so on. These are contrast patterns presented inside of rings. The rings differ in their eccentricity, which is their distance from the fixation point. And there's a total of 6 different rings here. And these are coming in a, as you can see, a pseudo-random ordering scheme. So that being the experiment, we can take a look at one of these design matrices. So the format here is a binary kind of onset matrix where all the values are 0 except for 1s to indicate when each condition comes on. So for example, the first stimulus condition, stimulus 1, which is actually the the smallest ring closest to the fovea, its first onset appears at the 73rd time point. And again, the time points come in seconds. And so that indicates it is at this time point that the ring comes on, and as we mentioned earlier, it lasts for 3.5 seconds. And so you can see for the first stimulus, it has a bunch of different onsets, and they occur at these points in time in the first run. And the same thing happens for the other stimulus conditions in pseudo-random fashion. So we have a specification of the experiment and design. We also have some scalars. The stimulus duration is 3.5. The TR, as we mentioned, is 1 second. And we also have these two other variables, which we'll talk more about later. Oh, and one last thing. BC stands for bias corrected DPI intensity. It's essentially the mean of each vertex's data, but correcting for some of the coil biases. And that's contained in this variable BC. So as you notice, the number of vertices contained in BC is exactly the number of vertices in data. And one other correspondence I forgot to mention, the number of time points, 368, is exactly what's in the data set. Okay, so that takes care of this data file. The first step, which I'll just go ahead and start running, let me change it to a directory here. We set up some basic options just to maximize speed. We set no denoising, so we're using GLM denoise to do a very simple GLM fit here. We're going to set the number of PCs to try and the denoising to 0, which effectively turns it off. We don't need a bootstrap, so we're just going to set that to 0. And so that just sets up an option structure, and then we call GLM denoise data. In this first case, we're just going to do nothing fancy. We're going to fit a vanilla or standard model that just uses a single href to model the response in each vertex for each stimulus condition. And we're going to pass the data in, the stimulus duration, the TR. This is important, indicating that we should use a kind of a generated based on a canonical href assumption what the time course should be like. And we're going to write some figures out to this folder. And the only tricky bit is this command here. So we're kind of on the fly going to expand this design matrix. So let's do a quick, even though it's finished, let's do a quick inspection of what that does. Temp, as you can see, has this general format of what design was, except that we have 36 columns instead of 6. And so the idea is each experimental condition gets split or expanded into 6 of them, because that's the argument we applied here. So let's just take a look. So figure 1 is the original design matrix with 6 different regressors, and now we have, after we do this transformation, 36 columns. So what's happened is the trials that occur for, say, stimulus 1 get split into 6 different columns. So 1 here corresponds to columns 1 through 6 on the right-hand side here. And so these trials get essentially randomly dispersed into 6 different segments. And the idea being that if we use this design matrix and we fit the GLM, we can get 6 different beta estimates for the same stimulus. And this will allow us to do some convenient post-hoc quantifications of like how reliable the response is to, say, stimulus 1. So each of the 6 stimulus conditions gets split into 6 different columns, and hence we get 6 times 6, 36 columns in the resulting design matrix. We're going to use this design matrix now, or I guess we've already done it, as we see here, and we're going to fit this very standardish GLM. So it's already done, and we can see the output in this variable called results st. There's a bunch of variables here. Most of them don't really matter. What we will do for now is to do some quick inspection of outputs just to ensure that it's reasonable. And we're going to use, because the data are prepared in vertices, it's very hard to look at unless you use a surface rendering mechanism. Here we're going to use a quick and dirty, almost a trick, but it's nice and convenient. It's an index scheme that essentially applies nearest neighbor interpolation so that we can render the vertices very conveniently. The basic gist is described in this previous paper that we published. Here's a little figure. Basically, vertices, after you flatten the cortical surface out, still are irregular with respect to the image. And so the image being defined as pixels, the pixels correspond, if you're happy to do a nearest neighbor interpolation, they belong to a vertex, and once you determine the assignment of vertices to pixels, we can encapsulate that in a simple matrix. So here we have that in IMG lookup. Let's take a look at that. IMG lookup is just a image or a 2D matrix, and and we can take a quick look. So it starts to look like a cortical surface. This is a flattened patch in early visual cortex covering approximately V1, V2, V3. Outside of the patch, there's just a dummy value of 1 just to make sure it doesn't crash. But then within the patch, these are indices into the data, specifically the vertex format of the data. So these tell us for each pixel in this image where to get the data from, essentially. So let's go ahead and use that mechanism. We're going to take the results we want to visualize, these variance explain values, R-squareds, and we're going to use a simple indexing scheme using IMG lookup to create a matrix called temp. So temp is just a 2D matrix of now data coming from this variable. We're going to set the invalid pixels to nan just to make sure they don't cause any visualization issues. And then we can very simply use ImageSC to look at the results. Okay, so this starts to look like what we saw earlier, except that now the data are plotted. Let's just change the color map and make sure that we get square pixels. Okay, so this looks very reasonable. This is a variance explain map in a flat patch of left hemisphere early visual cortex. Alright, so let's move on to the next section, which is really getting towards performing the TDM method. So the first step is to get estimates of response time courses in a fully unconstrained fashion. And we're going to do that by fitting a finite impulse response model. So I'm going to go ahead and issue that command. Actually, I'm going to modify one command here so we can see some diagnostics. And I'll just go ahead and kick this off. So the FIR model uses essentially indicator variables, or like kind of binary indicator variables, to model every single time point in the response to every single condition. And we're going to again use our little GLM fitting mechanism, GLM denoise data, to do that. So the call looks very similar. The essential difference is this flag here, FIR. We're going to model 30 time points after the onset, so that'll give us a total of 31 time points. And here we're going to use a slightly different splitting strategy. Here we will split each experimental condition into 2 splits. So essentially we'll just get 2 sets of time courses out. Okay, so the command is done, and the outputs are contained within this little struct here. And what I did briefly earlier was this extra flag called want parametric. It's not critical for this script, and that's why I didn't put it in, but what it does allow us to do is to take a look at some of the innards here. So if you use this flag, it'll also give you a version of the results, and using a parametric method to estimate the betas. But really what I wanted to get out was the design matrix. So in this version of the results, this is the final design matrix that was used to fit the entire data set. So notice the number of time points here is 6 times 368, so 22. No, sorry, there were 4 runs, so it's 368 times 4, 1472. There you go. So you can see there's a bunch of columns here. And so let me kind of walk this through. So recall that there were 6 conditions. They got split into 2 versions of each other, so that's 12. And then we're modeling 31 time points total. So onset plus 30 after. So that should be 12 conditions times 31. So this is 372 parameters to describe the stimulus evoked responses. So that you can see that it kind of makes sense here. 372 stops about here. The last several columns are just low frequency regressors. So these are polynomials. As you can kind of see, this is constant, linear, quadratic, cubic, or quadratic, cubic. Yeah, sorry, this is constant, linear, quadratic, cubic, and that's the first run. And then the separate set is used for the second run, third run, fourth run. Okay, so those are low frequency kind of nuisance regressors, but what's important are these regressors. So let's just zoom in on the first set here. And in fact, there's so many we need to zoom in further, otherwise we get strange aliasing. Okay, my gosh, we had to zoom in a bunch. Actually, let me zoom out a little bit so we can see. Okay, it looks like we'll have to zoom in even further. One trial. So this is pretty standard to fit a finite impulse response model. You essentially expand out the onsets into essentially lines. Okay, let's just zoom in like so. Almost there. Okay, so the first trial for the first condition, I believe we've zoomed in correctly. Actually, let's just do something like this. So let's just explicitly set the range from 0 to 32, 34, and set it from 70 to 105. Okay, much better. So the first stimulus got expanded into 31 different columns, the first stimulus condition, and this models the onset, so what's the response coincident when the stimulus instantaneously came on. This models 1 time point afterwards, 2 time points, 3 time points, and so on, up to 30 seconds after the onset. And so that's the structure, essential structure, and this gets repeated for every single trial that the stimulus occurred on. So it occurred there, it occurred there, it occurred there, and so on. And this next set corresponds to the second split corresponding to the first stimulus. So remember, there was a condition split, and then there was this expansion into these kind of binary indicator regressors. Anyway, so that's all fairly standard. And I just wanted to show that just to give it some sense as to what's going on. Okay, so we have fit this FIR model, and that gives us a bunch of response estimates. As you can see here, there's a lot of vertices. There were 6 conditions. We split them into 2, so now there's 12. And then for each of those, there's a 31 data point long time course. Okay, here we have a little inspection just to make sure we understand what's happening. Let's go ahead and evaluate that. So fairly simple code here. I've already pre-selected this specific vertex, and we just do a little loop so that we plot out from that variable I just pointed out a second ago. We pull out the time courses and we render each condition, of which there are 6, in a different color. And notice there are 2 traces, as kind of commented here. There are 2 traces for each stimulus condition because we did split the conditions into 2. So for example, there are 2 cyan here. And you can kind of see, and I mean the primary use for this is you can see the noise level. If you only have one response time course, you're really just guessing what the noise level here is. But here we have 2, so we can already see, even for this voxel, which was selected to be reasonably looking, the noise level is somewhat high. There's some uncertainty as to what the actual response is to different stimuli. But things look reasonable, and that's good. Okay, so we have a bunch of time course estimates. This next step is just some busy work, essentially, to extract or select vertices that we want to perform TDM on. Essentially, there's no point into putting in noise into the algorithm, so we have to apply some sort of threshold to find reasonable vertices. Here we use a simple automated method to find a reasonable variance explained threshold. You can see a histogram of all the r squareds. So sorry, I went through that quickly, but r squared is a field within this struct. It's a variance explained value, one number for every vertex. We're going to use this little function to determine a threshold. So the histogram of all the r squareds is shown in black, which you can kind of see there. And if it's essentially a mixture of Gaussians, 2, where the number of Gaussians is 2, it fits that to try to optimally fit the distribution, and it's going to decide to use a threshold here, approximately 35. essentially separating the two distributions that are summed to approximate the original distribution. So anyway, so this is a threshold, 35, which is now stored in this variable. Great. And we're now just going to use that to pull out those vertices and also pull out those vertices, their bias-corrected EPI intensities. Okay. Now we're ready to go and actually do the core technique, which is implementing this function called extract href manifold. A little bit of prep work. We're going to define an option struct. In this case, it doesn't actually have anything because we're going to use all the default values. Here, the format of the time courses that TDM needs is slightly different than what we have. So we're going to prepare these time courses. There's a simple step here. We're just averaging over the two condition splits that we have. So recall that we got time courses from fitting the FIR model and then thresholding and then extracting the time courses. So here the dimensionality was vertices by 12. And for this instance of applying TDM, we don't really need the separate condition splits, so we're just going to average over each successive set of 2 and divide. Well, this blob sums over groups of 2, and then we just divide by 2 to take the average. So that's what's happening there, and then we do a simple reordering of the dimensions. So now we have vertices by time points by conditions. So there's a fairly large matrix, but that's okay. And temp is going to be passed into the function. We're also going to give it the bias-corrected intensity values that correspond to these vertices. And the TR, it's going to save out some figures in here, and we're just going to give it the options. So let's go ahead and run that through. It actually doesn't take terribly long, and I think most of the time, at least for this instance of calling a TDM, is dedicated to generating figures. Okay, so it's done. And it did write some figures out to this folder, which happens to be this folder. Well, it's getting synchronized to my computer. And let's give it a second to finish the sync. And we're going to just take a look at some of these figures. So that's what the script does in MATLAB's little syntax here, but let's just directly pull up some of these figures. And that's fine. So there's 3 figures, manifold, model fit, and time courses. And these are reminiscent of the figures in the paper. Essentially, they are the figures in the paper, just in their kind of raw output format. And so let me just briefly talk about these. This figure shows kind of the data quantities and the kind of summary of what the method performed. Density is like a probability distribution of the time course shapes that we observed in the data, which, if you recall, came into the function through this variable here. There's a high density up here, there's some spread, obviously there's noise, and importantly we have these ellipses. This is the 2D Gaussian fit that's been performed, and these dots indicate the early, which is in black, and the late time course, which is just along the principal axis here. And the magenta is just where the first principal component of all the time courses lives, and in this case it's exactly with the pole of the sphere that we're facing, that we're looking down on. Anyway, so these the ellipses and the dots kind of summarize the results of the method, and it's plotted also here and here, just for convenience. So density is the kind of distribution of shapes. Vector length summarizes essentially the amplitude for different time course shapes using the same type of visualization and binning scheme. And EPI intensity is essentially the same idea, but applying it to the bias-corrected EPI intensity values that we fed into the algorithm, if you recall, BC values. BC values is not used to determine the ellipse in the fitting, but it's supplied to the algorithm so that it can give you these visualizations to kind of give you some sanity checks on what the algorithm is returning. So as you can see, the ellipse fits fairly well, the density and the vector length, and we'll see more details in a second. And also you can see the early and late time courses. You can kind of see this kind of low frequency darkness here. It's a little bit noisy, but you can see that the gray dot is nicely positioned in kind of the center of all this dark region here. So this gives us a bird's eye view of the sort of sanity of the process. This other figure gives you some details on the fitting process. This is a replotting of the density. This is the same thing after a bit of regularization. Essentially, you get rid of kind of the background noise level, so it just subtracts a constant. So that's kind of one component of what we're calling the data. The other component is the vector length. Here we just plot the vector length information after the regularization process. And then the average of these two gives the final, which is what we're calling the data in this context. And we want to fit this data using a Gaussian just to extract its principal structure. And you can compare these two images and they look fairly reasonable. This is a nice summary of what's happening in the empirical data here. So this gives you sort of diagnosis into how the data look and how the model is doing in extracting the relevant characteristics of the data. And then the third figure gives you some time courses. So if we blow this up, we see the three principal components. They're labeled basis 1, basis 2, basis 3 in red, green, and blue. And in fact, the magenta is actually identical to the red. So really we see magenta, green, and blue. So you can see a magenta looks like a canonical positive going bold time course. And we also have green, which is shown here, and then this blue thing. So these correspond to the axes of the space. Let me just remind you, PC1 is towards your eyeball, kind of the axis coming out of the screen. PC2 is this direction, left-right, and then PC3 is up-down. So that's the meaning of the time courses. And then we also have now plotted the identified time courses in black and in gray, which is the same color scheme here. And you can see black, the peak and the half max width are plotted with these black dots, and then the same is done for the gray time course. So looking at the black and gray time courses, they look pretty reasonable. Probably not as good as we can obtain had we used all the data, so like all depths, all 9 runs, all the vertices. But that's okay for this example. We have these time courses, and so they look pretty reasonable. Okay, so those are just the figures that were output by calling extract href manifold. They look pretty reasonable. And the final step now is to use those time courses to refit the data. So that's done in this next section here. So let me go ahead and run these next few commands. Okay, so all we've done is we've decided for our final sort of GLM fit, we're going to use 6 condition splits. So we just repeat this command, which we had done earlier. And here we manually convolve in the 2 time courses with the design matrix. It's a simple for loop where we just use conv2 to convolve each time course. So the time courses are in EL-href, which stands for early late, in this results struct. As you can see right there, there's 2 time courses. And it just ensures that the size of the design matrix that we get out is the same as we started. So here's how that looks. So we've just visualized the first run. So this is the convolved design matrix for the first run. Notice there's 368 time points as usual. And we see visually, at least there's 2 groups of columns here. And so the first group corresponds to the early time course. The second group corresponds to the late time course. And we can visually track that. So if you notice here, there's an onset roughly there, and then we can kind of see its counterpart over here. So these are highly similar but different, and this is just a visual depiction of the kind of up and down behavior of each of the time courses. So just to recap, conceptually, each regressor has been split into two versions. One has embodied in it the early time course. The second one has embodied in it the late time course. All right, so then we'll just call glmd noise data. We're using this design matrix that we've constructed, design 0. And we're going to now call it with the flag assume. But we're going to tell it what href to assume. We're going to use an href that's just a 1. So it's going to convolve it with a 1, which doesn't change anything. So it's a bit of a hack to get it to do what we want, but that's okay. So let's go ahead and call that in. So it's going to use our new constructed design matrix. I guess theoretically we could write a function to kind of hide this logic, but leave that for later. So the call is very similar, same old arguments. We already talked about what assume1 means, and that's it. So fairly straightforward. It shouldn't take too long. And then we're going to kind of look at the outputs. Okay, so it's done. Let's query what the results look like. The primary output of interest is in here. These are the betas. So just a comment on the dimensionality. Recall we had 6 original conditions. We split them into 6. We split each of them into 6, so there's 36. And now we have 72 because the first 36 are for the early time course and the second 36 are for the late time course. So these are betas, which we want to visualize now. So we're going to do some massaging of the betas. You can read that at your leisure. Let's go ahead and do that. Nothing crazy is happening yet. And now we're just going to visualize some of the betas. Let me go ahead and run this, and then we'll talk about it. So here was a really quick method to visualize what these betas look like across the cortical surface. As mentioned here, we're really just looking at the first of the 3 depths that we've provided in the example data set, which is actually depth 2. So this is close to the CSF, so it's outer cortical depth. And what we're looking at are 2 versions. They correspond to the rows. So the first row here is the early beta weight, or the early loading. The second row is the late loading. And the columns correspond to the different stimulus conditions. So remember, there are 6 rings. They proceed from foveal to moving more peripheral. And we're using a hot-cold color map to represent positive % bold change and negative % bold change. So you can kind of see by eye here this progression of foveal to periphery representation in early cortex. That's exactly what we expect based on the organization of early cortex. And you can also observe in the late loading kind of, you can see some semblance of the retinotopic specificity, but there's also a lot of kind of mess up here, as you can see there, and also down here. There's very high % signal change happening. To kind of diagnose that a little further, I'm going to jump this next section and show the bias-corrected EPI intensity values. So here, although the layout's a bit off the screen, but you can kind of see, let's take this one. Actually, I should resize this window somehow. Set figure pos. Let's just make it 600 by 600. There we go. So we have 3 cortical depths prepared in the data set. So this is what we call depth 2, depth 4, depth 6. Depth 2 clearly has a lot of susceptibility effects, likely indicating where the veins are. And you can kind of see in this portion here, this kind of darkening, and also at the bottom of, or in the mid to bottom, you see some darkening there. And that probably corresponds to, as you can see, these hot spots here, and also these kind of very large % bold changes here. Of course, you would have to do this comparison more carefully, but it does look by eye that they roughly correspond. Okay, let's run the bit that we did not do earlier. So this is just a visualization of what we're calling peak eccentricity. This just summarizes the 6 numbers into 1 number to give an estimate of kind of what is each vertex's preferred eccentricity tuning. So it's done using a center of mass calculation. And again, it's off the screen, but let's bring this down. And what we see are 3 depth preparations, so depth 2, depth 4, depth 6, and then the 2 columns correspond to the early beta weights and then the late beta weights. So the early ones look fairly nice. There's a nice progression. By the way, this cortical patch actually cuts out a bunch of the fovea, but that's okay for the sake of this example. We see this progression from small or low eccentricities to increasing eccentricities moving in the posterior to anterior direction. Whereas it's not terribly clear in the late loading. There is a hint of some tuning in the most superficial preparation for the late beta weights here, and then it kind of falls off, moving towards the white matter. Alright, so things look okay, and then the last bit of this script is really just an example, if you are curious, about this sort of ICA-based procedure for deriving these time courses. I'm going to go ahead and just run it. The overall structure of the call is similar, the major difference just being the outputs are not embedded inside of a struct, but you just call this function, you give it the time courses. One difference is this procedure that we've designed does need a test-retest of the time courses, so it's in the splits. And really that's the reason why we ran the FIR model with the 2 condition splits way back up here. Anyway, we provide those splits to the algorithm, and we put that in this variable, and we pass it in, and we call it, and it does its thing. And once it's done, we can see if it has done something reasonable. We talk about in the paper our thoughts on the nature of ICA and how that compares to the TDM technique. Here we go, it's done. We can do a simple inspection. There's some semblance of an early and late time course happening, and that's primarily the nature of how we kind of cobbled our heuristics on top of the ICA procedure. It looks a bit noisy. It's a little hard to say without further inspection. Anyway, so it worked in a sense, or at least in the sense that it didn't crash, and it's something. So of course you could think about this more, or maybe use these time courses in a decomposition procedure, kind of like what we did here, and so on. Alright, so really that was a lot of detail, and I just want to say, the core of what's happening is embodied in this line here. The other stuff was really just fitting GLMs, of which there are many tools and functions that one can use to do that. But the core is here, which is this method for extracting in an automated fashion reasonable time courses from a large set of time courses. Let's see if there's anything else worth mentioning here. These, not really. Okay, yeah, so taking a more bird's eye view, again, this example data set is just one of the sessions, and in fact not even all the data from that session. And we did provide, only 4 runs instead of 9, and only a small number of vertices. And theoretically, since this is a data-driven technique, the more and the higher quality data you give it, presumably the better the results. But I guess we have shown, even with 4 runs, it does look promising in terms of the reasonableness of the outputs. And I think that about covers it. Again, the details, in terms of the technical details, are all in the preprint, which you could take a look at. Let me just briefly point. So some of these figures should look familiar. This figure is essentially the manifold figure that we saw, that the code output. And we also saw a brief look at some of these types of maps, and we saw how to compute them, at least using this code. And those are quantifications. Yeah, all right, so that pretty much covers it.